There are over 1 million gifted and enthusiastic students who enroll in math programs worldwide every year.
But anywhere from 50 to 80% of them change majors or drop out of college before completing their degree, significantly more than any other field of study. And an overwhelming majority of students cite the same reason for this decision. What is this reason? And why do so many students give up on their math majors after they enter college?
Several weeks ago, I made this video about mathematics education and why people struggle with the subject so much. But let's circle back to this topic after we understand the big picture.
There are about 2,000 different majors available to students at the undergraduate level. Choosing the right one is not always so easy, especially with all the new challenges and social pressures accompanying the young adult life on campus. Many students weigh the pros and cons of several different choices, with questions like, what kind of job will I get after graduation? Or, how much do I enjoy studying this topic? And it turns out, about 1 in 40 undergraduates decide that a math major is what they want to pursue. These students often come from a strong background in high school math, where they've received good grades in courses like Algebra 1 and 2, Geometry, Trigonometry, Pre-Calculus, and Calculus. Some have taken the AP Calculus exam to receive college credit, and others may even complete more advanced courses if their school has them available.
Let's take a look at a sample problem, which illustrates how high school students think about math and what skills they learn prior to college.
This problem requires knowledge of calculus techniques and strong skills in algebra. Many students who excel in math during grade school have some combination of deductive reasoning skills, strong memorization skills, and excellent work ethic. Some have an innate talent when it comes to basic mathematics, but this talent only carries them so far. Everyone who succeeds at math eventually realizes that they have to put in considerable effort to learn formulas and apply them to new problems so that the solution method is forever ingrained into their brains. Once a student figures out a process to learn the material and memorize the formulas, they can apply this to any of the high school math courses like algebra or calculus, and they will succeed.
Math is hard. And when we overcome a difficult challenge, not only does it provide us with valuable life skills, but we actually get a dopamine rush, which makes us feel good.
So high schools across the globe are churning out these eager, young, aspiring mathematicians and sending them off to university programs with high hopes that they can apply the same techniques they've cultivated over the years to conquer the next level of math courses. But they are woefully unprepared for the challenges they will encounter in one introductory class.
While universities have differing degree requirements, most undergraduate math curriculums start students with the same courses and allow them to branch out to pursue individual interests in later years.
For example, the requirements at Princeton look like this. And you can see up there at the top of the list for core courses is real analysis. This is a class most math majors will take in their third year after completing the prerequisite calculus and linear algebra courses. And this is the mountain which math majors must overcome in their pursuit of a degree. Most don't make it. Real analysis spawns some of the most depressing Reddit threads and is the main reason why so many math majors fall short of the finish line. They change majors or even drop out of school feeling inadequate and depressed.
Why is real analysis such a challenging class? And why is it that some students succeed while others fail? Well, math is a language. You might have heard this from teachers in school or other YouTube videos. And real analysis is a proofs-based class. But to understand a proof, you first need to understand the language of the proof.
Most students who take this class for the first time have never had a course involving proofs before, turning them from the smart kid in their friend group into a toddler trying to learn the alphabet. This devastating blow to their ego can already be difficult to overcome, but couple that with the difficulty of the material, And it's no surprise that many students give up here.
Even those who make it past this first hurdle struggle to adapt their way of thinking to this new type of math.
In a calculus course, there is a certain type of structure to problem solving. First, you model the problem using formal notation. Then you apply techniques you learn to calculate a solution value. Proofs don't have this kind of structure.
Let's look at a very simple example to showcase this concept.
This looks so simple, right? Math students will easily comprehend the solution when they see it. But how did this solution come about? Could we have started off the proof by saying, all squares are rectangles? Well, yes, we could, but that wouldn't be a very useful first step. There are so many ways to start a proof, and the number of possible proofs is uncountably infinite. More importantly, many written arguments which seem logical at first glance are either circular in reasoning or lack rigor. Let's revisit the question of how did we write down this proof?
The answer is experience. Having studied hundreds or thousands of similar problems, we're familiar with the idea that 0 and 1 are powerful when it comes to multiplication.
0 absorbs any other numbers and turns them into nothing, while 1 itself is absorbed in multiplication. Recognizing this and using several of the field axioms of the real numbers, we were able to quickly reach a contradiction. And now that we've seen these ideas in practice, we can store them in our back pocket until a similar problem comes around.
This is exactly how students overcome the challenges of real analysis. By putting in hundreds of hours, studying thousands of proofs, they learn and master a new set of skills to help them solve problems, similar to the process of learning a new language. The more practice they get applying these ideas, the more refined their solution process becomes, and this will allow them to solve more and more challenging problems. Now let's circle back to the issue of how early mathematics is taught.
Because students aren't exposed to the ideas of rigorous mathematical proofs during grade school courses, they don't develop the tools needed to succeed in advanced courses like real analysis or abstract algebra. The teaching method of memorizing formulas and applying them is how we were taught to solve math problems growing up, and this is the way most of the world sees math. But for mathematicians, there is a beauty inherent to rigorous mathematical proofs, similar to that which an artist may find in a breathtaking painting, or which a writer may feel from the pages of a moving novel.
So if you're currently struggling with mathematical proofs, don't give up. There is light at the end of the tunnel, and it is well worth reaching it. And if you're thinking about majoring in math, brace yourself for what's to come. Maybe take a look at some books on basic proof techniques ahead of time. For everyone else, I hope you enjoyed this glimpse into the challenges of pursuing an undergraduate math degree. If you know anyone currently studying real analysis or struggling with abstract algebra or any other proofs-based course, show some sympathy. Math is hard.